Alright, hello, my name is Walter Hicks. I'm a student here at Kansas State University. I'm a civil engineering student. Today I'm going to be talking to you about Manning's equation, and it's a good topic for any civil engineering student to know, especially if you're going to take hydraulics or water resources class. But it's also really useful for a geology student also. You can use this value to find the velocity of water in a stream bed, and if you're interested in erosion effects, like most engineers and geologists are, this is really important to you and you use it a lot. So to go through this, we'll start off by telling you what Manning's equation is. Like I said, it's used to find velocity of water flowing through a stream bed. The caveat with that is it has to be an open flow stream bed, so it's only applicable to canals, rivers, and waterways. If you are trying to analyze a system that is close to pipe flow, this doesn't work anymore, and you need to use a different equation. Manning's equation is empirically derived, so what that means is that it was found by looking at how water in a stream bed behaves in the natural environment and then trying to come up with an equation that mimics that. So that's why we end up with an odd value here like this 1.486. So moving on, Manning's equation tells us that velocity is equal to this 1.486 over a value n. This n is known as Manning's coefficient. That is a coefficient that's unique to each stream bed material. So if you're looking at something that's concrete, maybe has grass or it's gravel, each of those values are going to have its own Manning's coefficient n. If you're wanting to do a very specific analysis, you might even do an analysis specifically on the environment that you're in to get a really accurate Manning's coefficient n. But lucky for us, in most situations, there's already dozens of different Manning's coefficients that have been found through thousands of different tests, and we can use those to our benefit and just apply those out of the table. The next value you come across is this coefficient for variable r. This is the hydraulic radius, and what that does is it relates the cross-sectional area of the stream you're looking at to its wetted perimeter. So if you look at this diagram, the cross-sectional area, of course, would be this distance right here, or this area right here, and that's simply the height of the stream bed, or the depth, times the width of it, so h times w. Now the wetted perimeter is slightly different from a typical perimeter because you don't count all the sides. You only count the sides of the stream that are in contact with the stream bed itself. So we have one bank on this side with a height of h. You have the bottom of the stream bed with a width of w, and then you have another bank on the other side with another height of h. So you add those all together and you get the wetted perimeter. So here we have 2h plus w, and that gives us our hydraulic radius. The last variable that's involved is slope, and slope is a very familiar concept to lots of people, and that's just the relationship of the change in height of the stream bed over the length of what you're analyzing. So when you take all of these variables and plug them into Manning's equation, the output is the velocity of the stream bed at the area of interest. So now we'll continue on and look at a worked out problem where we're going to find the velocity. Alright, so here we are with our setup Manning's problem, or Manning's equation problem. So I'll just read you the problem statement in case you can't read it there on the screen. It says, water flows steadily in a concrete canal with a width of 20 feet and a depth of 5 feet. If the canal drops 1 foot in height for every mile, what is the flow rate in cubic feet per second? So we're going to use our Manning's equation right here. Remember, V is equal to 1.486 over n times the hydraulic radius r to the 2/3 times your slope to the 1/2. So over here I've gone ahead and written out our constants, or our known values, real quick. Our slope is 1 foot per mile, and of course that's equal to 1 foot per 5,280 feet in length. My Manning's value, or Manning's coefficient of n, in this case, is 0.013. You can find Manning's values anywhere. I got this one out of a highway engineering book, but they're widely available on the internet and several different engineering manuals, so just go ahead and look through there. You might have to do some hunting to find the one that's appropriate. For concrete alone, there's a couple dozen different values depending on what type of concrete is used and how it's used, what kinds of things you use for the aggregate and all sorts of different things. So we'll just assume in this case that's going to be a 0.013. Then we calculate our hydraulic radius. and that is, in our case, the cross-sectional area, which is the depth times width, so 5 times 20 feet, over the wetted perimeter. So we have 2 height, 2 times 5, plus our width of 20 feet, and that gives us 100 feet squared over 30 feet. Also, we'll be using this a little bit later. Since we're asked for flow rate and not just velocity, we need to multiply the velocity we find with Manning's equation times the cross-sectional area of the channel, A, and that'll give us a flow rate at the end. So I've taken all of these values right here and plugged them back into our Manning's equation for velocity, and that gives us V is equal to 1.486 over 0.013 times our hydraulic radius of 100 feet squared over 30 feet raised to the 2/3 power. Then times our slope of 1 foot per 5,280 feet, so the 1/2. And once you plug that all into your calculator, we end up getting a value of 3.51 feet per second. And now that's just the velocity of our water. To find the flow rate, we're going to need to plug it into this equation, which is the flow rate is equal to cross-sectional area times the velocity. And in our case, our cross-sectional area is 100 feet squared. That came from depth of 5 feet times width of 20 feet. And then we'll multiply that by our velocity, and that'll give us 351 cubic feet per second of the flow rate in this concrete channel. Well, I hope you've learned something, and it's a very valuable tool, and I hope you can apply it to something in your engineering studies. Thank you.